All right, video number 2 for chapter 7. So we ended the last one talking about our different cell types. So these cell types are either going to build bone or remove the bone, particularly focusing on our osteoblasts or our osteoclasts that remove bone. So in order to build bone, our osteoblasts, our builder cells, are going to create the collagen protein. So going back to our rock candy example, the collagen would be the string. The minerals that are added to it, so mineralization, that is going to form on the outside of those collagen strands and create the hardness of bone. So for organic matter, just want you to focus on collagen. I don't care about the other ones for you to know for the test. The inorganic portion of bone, so if you remember from our chemistry chapter, organic stuff is carbon-based, inorganic is not. So the only ones that I want you to know for the inorganic is hydroxyapatite. So that is made up of calcium and phosphorus. So those are your main components. And then there's some other minerals in there as well. But the hydroxyapatite is one I want you to know, plus calcium and phosphorus. Okay, so that's inorganic, your minerals that crystallize on that collagen structure. Another way to call these two types of substances is our ceramic portion and our polymer source portion. So your minerals would be your harder ceramic, like a cup, like a teacup or something. Those minerals are the ceramic portion, the harder portion that allows our bone to support the body weight. The polymer portion is what gives our bones some flexibility so your body isn't rigid, and that's their polymer. So they're all proteins. Proteins are made up of our building blocks of amino acids, so there is some flexibility to your bones. So they don't shatter if you hit it hard enough. Okay, so in our compact bone, we have these particular structural units called osteons. And, okay, there we go. Okay, so in the center of these osteons, which is this circular structure here, so osteon here, circular structure, osteon here. And the center portion of that is your central canal. It's also called your Resorption canal. So this allows for blood vessels and nerves to run through the center portion of this long tube structure of your osteon. So that allows for feeding of your blood, also getting into our spongy bone on this side, allowing for it to get to all the portions of that organ. So our bone, each individual bone is considered an organ. So around our Resorption canal, we have concentric lamellae, so like concentric circles, so layers going around that central or Resorption canal. On the outside of our compact bone, so where we have those osteoblasts hanging out by the periosteum, we just continue building bone on the outside. So we have our concentric lamellae, so just extra additional layers that aren't exactly part of an osteon. So they're just adding more layers on the outside of bone, so like widening the bone. Anyway, okay, so inside our osteons, I'm over here reading my notes, and they're bad handwriting. We have our osteocytes. They're trapped in the lacunae, so all these little spider-looking things, and yes, you'll be able to see this in the microscopes in lab. Those little spider things, those are actually your osteocytes. Okay, spongy bone on the inside of compact bone. So remember, it looks like a sponge, but actually it's still hard. So this lattice structure made up of spicules and trabeculi, so different types of shapes so that you can build the inside to actually have the correct direction of minerals so you can support the weight. Inside all the gaps is filled with red bone marrow, so, or yellow bone if you're like full adult. But it can go back to red bone marrow, by the way. Okay, so that fills those empty spaces. So with your spongy bone, most of it is these two structures, very few osteons, no central canals. Provide the strength without all of the weight like you would with a compact bone. So with our trabeculi, that actually forms along your stress lines. So this is the top portion or more superior portion of a femur. So going back to my little skeleton dude. Make it a little closer. Okay, here we go. So that's a femur. That's where this head portion, that big round portion, is fitting into the acetabulum of your hip bone. So that's where the little hip socket is. So for that weight structure, you got weight coming from this side as well, weight coming down on top. And so the trabeculi actually will form in order to handle the weight. So from the top as well as from the sides. So inside the spongy bone, we do have bone marrow. We have two different types of bone marrow. So we have red bone marrow. This is the one that's going to produce our blood cells. And in an adult, in this little picture, so everything that is red on this picture is where adults will have red bone marrow, and so therefore blood cell production. The rest of it is yellow marrow. It can transform back to red marrow if you are anemic and you need more blood cells. Okay, so just an overview of our different layers inside of a bone, going from the inside out. We have our bone marrow. That is in between our bone marrow and our first bit of bone. We have our endosteum, so endo, inside. Then we have our spongy bone on the inside. We have our compact bone that covers our spongy bone. And then the last layer is our periosteum, so remembering perimeter on the outside. So that's what gets our different layers of bone. Different layers. Where are we at? 6:40. Oh, we're good. Okay. Okay, I'm going to move on to bone development. So I might be able to get this in 2 videos. Awesome sauce. Okay. Looking at actual bone formation. So the process of bone formation has a fancy term for it. We have ossification, also called osteogenesis. So remembering that bone is also called osseous tissue. A lot of times you will still see something that is the formation or creation of something. A lot of times they will use the term genesis for that. So that's kind of an easy way for some people to actually get that, or at least for a lot of people. Okay, so we have 2 different types of bone formation or ossification. We have intramembranous ossification that's going to produce flat bones. So for example, the skull, the clavicle, and the fetus. So our little brain freeze. Okay, I'll think of it later. What is that called? I don't remember. Okay, it's a clavicle. It has a normal name and I forgot what it is. Went blank. Oh well. Okay. Extra layers can also form to thicken bone so that you can handle more weight as you grow. Endochondral ossification is the other type, and that's for your lengthening of your long bones. Okay, intramembranous ossification. So remembering our osteoblasts that are hanging out inside the endosteum and periosteum. Long story short. So part of your embryonic layers of tissue, you have your mesenchyme, which is where you get your bone formation. So in that layer, you have a bunch of osteoblasts. They're going to continue to build bone. Eventually they become osteocytes trapped in lacuna. They're making these blood spaces smaller and smaller. Eventually you have a good foundation of spongy bone. You still have your periosteum, still got osteoblasts hanging out on the inside of that. So then they're going to create your compact bone on the outside of your spongy bone. You still have periosteum there. You can still thicken the bone widthwise. You also have these bone cells on the inside, so you can still do remodeling on the inside of that type of bone. Collarbone, that's what it is. Clavicle equals collarbone. Thank you. Okay, so here's just a microscope picture of it. So our periosteum, osteoblasts, we got some bone building going on, lacunae with osteocytes trapped in there. The other type of bone growth is endochondral ossification, and this is the growth of long bones. So here we have our little fetus with a bone, which is nothing but cartilage at the moment. So hyaline cartilage, so our glassy, very thin collagen layer, collagen fiber type of cartilage, surrounded by the perichondrium, which again has those osteoblasts. Okay, so here are chondrocytes. So these are going to be your mature cartilage cells. They're going to open up our primary ossification center. So what that's going to do is going to end up creating our bone marrow cavity in the center of that long bone. You can also make another one. So this is how you end up with a gap space in between your epiphysis at the head enlarged region of the bone and the diaphysis, which is the shaft region. So you continue making bones. So you make your spongy bone, and then you start creating the compact bone on the outside. You keep building bone. You end up with this hyaline cartilage epiphyseal plate. When that happens, you continue to just create more bone and lengthen the bone and create more length in that bone. I just said that. Oh well. Okay, eventually as an adult, that epiphyseal plate closes up, or if you start taking steroids, it'll close up faster. So you end up being short. That epiphyseal plate will become your epiphyseal line, is just a bony little scar to show where that used to be. Okay. So cartilage at our articulations, and then of course making up the bone. Bone keeps growing. By the time your late teens or early 20s, that's when your bones pretty much are fully developed. So if you are in my class, most likely, yeah, you're done growing. I'm sorry, you are not going to get into the NBA or WNBA unless you are just really talented. Okay, so you're not short, you're a People McNugget. Here is a x-ray of a child's hands. This is why they're so, again, flexible and they do weird stuff. Because all the little gap spaces that you can't see stuff in, that's where they're still not bone. So that's why they're all like weird and, you know, can still do like the gaming and their fingers are just a-flying because there's nothing there. Okay. So here's another one of a fetus skeleton. Again, places where there's gaps, there's nothing there. So that's why they're all like weird and flexible. Here's that little soft spot in the baby head where our cranial bones have yet to fuse together to form the skull. So protect the baby's head. Okay. Okay, so again, epiphyseal plate, that where we get our growth and length of our bones. We also can grow widthwise using appositional growth, so just creating additional layers on the outside of the cell using the osteoblast and the periosteum. So again, periosteum, perimeter. Okay, so bone remodeling. So we have two different types of bone remodeling. We have absorption and deposition, so like a bank deposit. So we either absorption, taking minerals away from the bone, deposition, like depositing minerals onto the bone. So it just depends on the stresses you put your bones on is going to determine what happens. Okay. So there is an exchange of minerals between your bloodstream and your bones. And it's based off the bone cells doing their job. So we have deposition, so mineral deposition made by the osteoblast. So they're going to produce the collagen fibers. Those collagen fibers become mineralized using, again, our hydroxyapatite, which is our calcium phosphate crystal, which is most of what our bone is. So by creating collagen, we'll remove those minerals and take them from the blood to the bone. The opposite situation is mineral resorption. So we're taking minerals away from the bone. So this is our osteoclast. So on this ruffled border section, the osteoclast is going to release hydrogen, so pump hydrogen from the cell out into what's called the resorption bay, so this little area here. When it does that, hydrogen is positively charged. So we'll talk about this in acid-base balance and electrolyte balance at like near the end of AP2. But Chloride is negatively charged. So remembering from chemistry chapter, opposite charges attract. So chloride's going to be attracted to that positive charge of hydrogen. So it's going to flow out of the cell too. So since you have all these extra solutes hanging out in this resorption bay, water's going to follow by osmosis. So when that happens, we create hydrochloric acid, so very strong acid. What is that going to do? It's going to desorb the minerals. Then, once those minerals are absorbed, or dissolved, then a acid protease, so an enzyme, is going to break down the collagen. So in this case, we're taking the minerals from the bone and adding it back to the blood. Okay, so with our skeleton basically acting as a mineral bank, it also helps with calcium and phosphate homeostasis. So we're going to focus on calcium first. So the reason why we need both calcium and phosphate is because phosphate is part of our different nucleic acids, our phospholipids that make up all of our cell membranes, and works as a buffer for pH, so maintaining our body's correct pH. Calcium, what do we need that for? We'll talk about this later, but it's necessary for neuron communication, muscle contraction, blood clotting. We won't really talk about that one as much. And exocytosis. So our body needs to maintain certain levels of this. So if your body doesn't have enough of this in the blood, it will steal it from your bones. Okay, so exchange, there is a normal level that it likes to keep. So depending on how much you take in through your diet, how much is lost, how much is exchanged with your bone, and it's regulated by 3 different hormones. So we have calcitriol, calcitonin, and parathyroid hormone. Oh, look, it's the skin again. So with our calcitriol, which is a form of vitamin D, we take cholesterol. The skin is going to convert a precursor cholesterol type of molecule using the UV radiation from the sun. Does the first step. Liver and kidneys do the rest of them. Make our final calcitriol. That's going to affect your level of calcium in your bloodstream. So how does it do? What does it do? It's going to raise your blood calcium level. So it's going to increase calcium absorption in the small intestines. So increase from the diet into the bloodstream. Also increases calcium resorption from the skeleton. So what it's going to do is stimulate the production of more osteoclasts. Osteoclasts being our bone dissolvers. That's going to remove bone and put those minerals into your bloodstream. It also promotes kidney reabsorption. So as your kidneys are filtering out your blood, keeping more of that calcium back into your bloodstream. So taking it back out what was filtered and less of it's lost to urine. Okay. We're still in calcitriol? Yep, it is. Okay, cool. Okay, so necessary, making sure we have enough calcium so that you can continue to build bone and keep them nice and strong. If not, you have either abnormal softness, which causes the bones to bend, and so you have rickets in children, where that's misshapen, or osteomalacia in adults. That's why grandma's all hunched over, because her bones have softened, and so with the extra weight and pressure, they start curving over. Okay, next one, calcitonin. So this is from your thyroid gland. So it's going to lower blood calcium level by stopping or inhibiting your osteoclast, so less bone resorption, so less removing of bone and putting it into your bloodstream. It's going to stimulate your osteoblasts, so more bone building, more collagen production that gets mineralized. That mineralization is going to take calcium from the blood, stick it to your bones. Okay, may also inhibit bone loss in people who are pregnant, since they're building a kid. That kid needs a whole skeleton, so keeps you from your body stealing it if you're not getting enough. And women who are lactating, because some of that calcium is going to come out in the milk. I'm going to skip this just for the sake of the length of this video. That's just showing you the feedback loop on that hormone. Okay, next one, parathyroid hormone. So our last hormone for calcium is going to raise calcium blood levels. It's actually going to help out the effect of calcitriol, helps with absorption in kidneys so that you're not losing it to urine, increase your osteoclast, so you're going to have more bone resorption, so more removal of minerals from the bone, and inhibits collagen synthesis by osteoblasts, so less building of bone, so less calcium being taken from the bone, less calcium taken from the blood and being put into bone. And again, more feedback loops of that, so looking at that in a picture form. Okay, so this is just showing different parts of the body and which hormones are affecting which ones. Okay, we're almost done. This is the last slide, well, second to last slide, whatever. Okay, so with our phosphate portion, that's also regulated by hormones, just only 2 of them. So calcitriol is going to raise phosphate levels by promoting absorption in the small intestines. Your parathyroid hormone is going to lower phosphate levels by promoting urinary excretion. So more of it's going to be lost to urine. So here's a chart that kind of puts everything in one slide. Calcitriol, calcitonin, and your parathyroid hormone. So where is it produced? What's the effect on blood calcium level? How does it do it? Also looking at your phosphate level. So what's the effect on blood phosphate levels? Calcitonin, of course it does nothing, so that's why it says none. And how does it do that effect on the phosphate levels? And that's it, at least for your study guide. So I'm going to cut it here. See you next time.